last time you have to watch one of my videos, at least this year. Who knows what happens with everything next year? But last one I'm making. Thank you to Mrs. Higgins because she's kind of covering more of the last week stuff while I'm being lazy, laying around, not doing a whole lot. But I apologize if I kind of recover some stuff that she's already done. I'm like way in advance, like a week and a half before I think you'll be watching this. And so we're still, we haven't talked a whole lot about which things, what days, and all that kind of stuff. But we're going to look at some Q equals MC delta T stuff. I'm going to do a reaction, generate some energy. This is potassium chlorate. Potassium chlorate is a better oxidizer than oxygen. So if you imagine from the name of oxidizing agent, right, if something is an oxidizer or an oxidizing agent, it is really good at causing reactions that are kind of similar to when oxygen reacts with things, right? It actually turns out that it's about electrons, not about oxygen, we learned. But oxygen was the first thing that we kind of looked at with those, so we call it oxidizing agents. This is a better oxidizer than oxygen is, right? So if we think about stuff burning, like logs burning and fires and that kind of stuff, this is better at helping stuff burn than oxygen is, right? So we're going to take a gummy bear. Don't tell Mrs. Higgins. I forgot to bring candy, so I went down and raided her room because I know that she keeps candy around. So this is one of those little German gummy bears. I weighed this little guy, and he is 2.5 grams. So if you remember from health class, or if you watched the whole other video like you were supposed to, 1 gram of sugar stuff. And I think we can agree a gummy bear is pretty much 100% sugar, right? It's not 100%, but 2.5 grams. Each gram is 1 big C calorie, right? And remember, a big C calorie, 1 food calorie, is 1,000 little c calories. So if I want to write out the work for all of it, 2.5 grams of sugar, and it's for every 1 gram of sugar, it is 4 big C calories. That's about 10 big C calories, or 10,000 chemistry calories, right? 10,000 calories, and you can't read that at all. That says 10,000 little C calories. I'll move the computer forward for when we're going to actually work problems and stuff. But so I'm going to heat this up, and I'm going to get it to release that energy in a different pathway than your body does. But remember, the beginning and the end is still the same. Even if I take a different pathway, we're still going to go from sugar to carbon dioxide and water. So when we do that energy graph, even if the bumps in the middle and stuff are different, the beginning and the end will still be the same. So it's going to release the same amount of energy it does in our bodies. So it's going to release right about 10,000 little c calories, or 10 calories, right? So you think about this, and you're like, well, that's not a whole, I grabbed the red one before. It doesn't really matter. 10 calories doesn't seem like a whole lot of energy. We'll see what that looks like here. This is more reactive, a better oxidizer than oxygen, but it's a solid. Solids don't react real well. So I'm going to heat it up to turn that solid into a liquid. This is ionic, so you've got to get it pretty hot to melt it. It is one of those ionic things that has a low enough melting point I can melt it, but it's still got to get pretty hot. Oh, I never goggled up for science. F- for Mr. Fred. Normally I've got students that remind me of that because I forget everything. All right, so we've got a nice liquid here, right? I don't know how well you can see that, but we've got a nice liquid. I'm going to go ahead and kill the lights. It is splattering stuff all over the place. Makes a mess. That is smoke everywhere. Notice here at the end, it burns a little different. That's the more, what's the horse hoof stuff that they use? It's like an auger type material that they use to make gummy bears and stuff. Collagen? Collagen, yeah. The collagen burns a lot slower there at the end. So you definitely saw how that changed at the end. My room is completely filled with smoke. You can hear this guy still. Oh no, where's the microphone? Microphone's right here. You can hear that. And here, lean in, you can smell that. You can't smell that. Did you really lean in and sniff? No, but if you could, it smells like roasted, burnt marshmallows, right? So that was 10,000 calories, right? That was 10 food calories, right? So you think about popping gummy bears and stuff, we are horribly inefficient machines, right? The amount of energy that our bodies use every day is a massive amount of energy, right? So 10 kilocalories, it's so foggy in here, I can barely see the computer. I'm going to pause it for a minute and let the smoke clear out, and then we're going to work some problems with that, right? But 10 calories, actually quite a bit of energy. All right, it still smells like burnt marshmallows and roasted marshmallows in here really strong, but cleared out a little bit of the fog, moved you forward so you can actually hopefully see the board a little bit. We've got 10,000 calories. Calories is a unit of energy just like joules. Joules is the SI system. Calories is the metric system. That is also the one that we use here in the States for food energy stuffs. But if you were in Europe, they wouldn't talk about counting your calories for a diet. They would talk about counting your joules for a diet. And as I understand it, in Europe, they do go ahead and use joules for stuff. So for food energy stuff. So let's go ahead and solve a problem. Let's say, how much water could we have just heated up by, let's say, make it hot chocolate, right? So if we're going to make it hot chocolate, it's going to go from about 20 degrees Celsius. You're probably going to want that to be maybe probably about 45 degrees Celsius. Right, so my change in temperature there would be a positive 25 degrees Celsius, because final minus initial, just like the delta H is products minus reactants. Well, delta T is final minus initial, so 45 minus 20, it's going up by 25. Well, that energy that the gummy bear released, right, we could capture that energy by the water. So the gummy bear released the energy, the water could absorb the energy. So the water is gaining 10,000 calories of energy. So we're asking, what mass of water could we heat up that much? Water has a specific heat of 1 calorie per gram degree Celsius. You should write down water's specific heat in 2 different unit sets. Calories is 1 calorie per gram degree Celsius. That's what it's defined as. Joules is 4.184. Well, I could change my calories to joules, but then I would just use the specific heat in joules and it would cancel back out, right? So mathematically, I took my eraser home so I could use whiteboards when kids got on Google Meets, and now I don't have an eraser. Mathematically, right, we've got Q equals MC delta T. I'm solving for mass, so it's going to be Q divided by C and delta T, right? Because I want to get mass by itself, so I divide both sides by C. I divide both sides by delta T. And that's going to equal the mass. So the Q is 10,000 calories divided by 1 calorie per gram degree Celsius. Now, we have to make sure with our calories and our specific heats, we're dealing with chemistry calories and little c calories here, not kilocalories, which technically our food calories is a kilocalorie. And our delta T is 25 degrees Celsius. So we're going to go 10,000 divided by 25. 10,000 divided by 25 gives us 400 grams equals our mass. 400 grams of water is how much we could heat up to like a hot chocolate temperature, right? Not boiling, but warm. Body temperature is 37 in Celsius. That's a little warmer than that. So probably, I'm just guessing. I don't know how hot you really want that. But 45 seems like a reasonable temperature there, right? So you make sure your units match. Make sure your delta T is final minus initial. Are you going up or down? That kind of thing. We'll work one more problem with this. So let's work another problem. Let's say you have a pound of copper, right? So this is nowhere near a pound, but 454 grams is a pound. Let's say you have 1 pound of copper. I want to know how much will you heat it up? What's the change in temperature, right? Heat is different than temperature. Temperature is a measure of average kinetic energies. How fast is this stuff moving? Heat adds in the idea of how much stuff is there, what's the specific heat of that stuff. This is more an idea of heat, right? So heat is really a flow of energy. So if something doesn't have much mass, it might have a really high temperature, but it still wouldn't have a lot of heat. If something has a lot of mass and is only a little bit warmer than room temperature, it can't transfer that much heat, right? Because it still is a small temperature change, right? So temperature and heat are a little different. But let's say how much could we heat up that copper? Well, you don't probably know. Oh, it's not listed right here. I thought they had copper right here. Well, let me look up the specific heat of copper, right? There is in your book, there's a bunch of them like iron and all that kind of stuff. I thought they had copper there. I think copper is 0.2, but I'll double check. So copper's specific heat is 0.385 joules per gram degree Celsius. Hopefully you recognize a problem with my energy is in calories. So if my energy is in calories, we're still getting a glare on the board. 0.385, 454, 10,000 calories. Well, I've got calories and joules right here, so those aren't going to cancel out. So let's change one of those. I'm going to go ahead and change my energy to joules. So to do that, we just say, well, for every 1 little C calorie, it is 4.184 joules. Write that down on a note card. For these, you'll need to be able to convert back and forth. So that's going to give us 41,840 joules. 1 pound, 454 grams of copper. Copper specific heat is 0.385. So Q equals MC delta T. Divide both sides by M and C. So Q over MC equals delta T. That's going to give me my change in temperature, not my final temperature. If they ask me about my final temperature, then I would need to add my initial temperature to it and stuff, right? So 41,840 joules divided by 454 grams and divided by 0.385 joules per gram degree Celsius. So 41840 divided by 454 divided by 0.385 gives us 239 degrees Celsius is my change in temperature, right? So if we started at 20, then it would have ended at 259, right, instead of 239. So 239 degrees Celsius is my change in temperature there, right? Copper has a pretty low specific heat, so it heats up and cools off pretty quickly. We can actually see some evidence of that. So we can see some evidence of this with our copper wire here, right? Now, if we think about my Q equals MC delta T equation, would this little bit of wire right on the end here have much mass? It's a pretty small mass. Copper has a low specific heat. It heats up and cools off quickly. That's one reason a lot of cooks like copper pans, because they heat up and they cool off quickly. Right? And so then if I add some heat to it, will the temperature change quickly or not so quickly? Right, can you see that? Yeah, we can see that, okay. So I'm going to put this copper wire in the flame, leave it there for, what is that, about 5 or 6 seconds, glowing red, and look at that, it can burn right through the paper. But look at that, oh, now it can a second time, gotta do it a third time. It can't do it. It's already cooled off enough that it can't burn that, right? I need it to be far enough away so you can see the flame, but I feel like this is a little too far away. Again, heating it up for just a few seconds. It is at a very high temperature now, right? You can see it glowing red. But when it comes out, the Q there is not huge, right? It doesn't take that long to cool it off because the Q is actually not that much. The mass of this copper wire is not all that hot or all that high, right? It's a low mass, it's a low spin heat, so it heats up and cools off quickly. And in just that much time, I can touch this. Now it's still hot, but it's not like so hot that it's burning me. And just a few seconds ago, it was burning paper. Can you see the holes in the paper there? Right? So I think that's kind of an interesting example. The ocean is like the opposite of that, right? The ocean is huge, tons of mass. It takes forever to change the temperature of the ocean, right? Takes a long, long time, right? So you can see that paper burn there. So when climate scientists talk about, oh, well, the ocean has changed to, 0.2 degrees or whatever, you're like, well, 0.2 degrees, who cares? Well, the whole mass of the ocean, and the ocean has a huge specific heat. So that's a lot of energy that the ocean has absorbed there, right? So hopefully that helps with working a few of those problems. I talked too long. I'm sorry, 14 minutes is a long time.